Hi, and welcome back to another episode with It's Dr. Dan. And today we're going to be looking at the law of partial pressures. So, the law of partial pressure was originally made by Dalton, which essentially states that if I have a bunch of individual gases that are all in the same container, so I have all these different gases. So, if I take the individual pressures of each gas and I add them all together, it will be the sum of the total pressure. So, what that kind of boils down to is a law that looks very, very similar to this one. So, we have P total, which is all gases in your container, plus the first gas, the second gas, third gas, and so on. So, this is just telling you pressure of an indice, meaning as infinite number of gases that you could possibly want in your problem. So, we just simply add them all up. So, kind of the idea is, let's say if I blow into a balloon and I blow air into that, well, air that's coming out of you is going to be what you're exhaling. So it's going to be CO2, possibly some oxygen, nitrogen, a mixture of trace gases that are going to be in the air. So let's take a look at air and try to get an idea of how we can do a sample problem of this using this formula. So if I say that I have a sample of air and it has a volume of 19 liters, and it contains approximately 78% nitrogen, 22% oxygen, and I'm telling you the temperature of this sample is 28 degrees C. Determine the total pressure of each gas. All right, so percents. Oof. These are always really, really hard and a little scary whenever we have anything with percents. So whenever we have a percent problem, the one thing we got to remember is the word percent. So telling you that it's out of 100, and we can represent this as many different things as we want, whatever units. So in this case, being that if you know 78 and 22, it equals 100. So that seems to be pretty convenient for ourselves. So what we can essentially do is, if I have 78% of nitrogen, that's the same thing as saying that, I have 78 grams of nitrogen by mass in a 100-gram sample of air. So it's that percent. So we can do that for nitrogen, and we can also do that for oxygen as well. Well, okay, so if I have both of those, well, what is something that's really useful to convert to when we have mass? Well, what's always our goal in terms of a lot of our different calculations? So one thing you're going to hear me say in a lot of different videos on this channel is the goal is the mole, meaning that if we can convert to moles, we can solve for almost anything, which makes it really exciting. So when it comes to chemistry, our goal is always the mole. So how do we get to moles with a mass? Well, that always revolves around using molar mass. So what we have to do is look up our molar mass using our periodic tables for both nitrogen gas and oxygen gas. So let's first start with nitrogen. So we have 78 grams of nitrogen. We're going to set up a T table for ourselves. And if you look at your periodic table, you'll see one element of nitrogen is 14 grams per mole. We have two of them because it's a diatomic. So it's going to be a total of 28 grams of nitrogen for every 1 mole of nitrogen. And once we do that, we can see, grams cancels grams, leaving us with only with moles. So when we only have moles here, well, all right, that's very, very useful for ourselves. We can convert that. So once I do that math, so 78 divided by 28, you will get 2.79 moles of nitrogen. All right, that's something. Now let's do the same thing for oxygen. Well, for oxygen, I also have 22.0 grams of oxygen. We'll set up a table for ourselves. And when we add up 2 oxygen atoms, that's a total of 32 grams from our periodic table of O2 for every 1 mole of O2. I'll do the same math. So 22 divided by 32. And what we are going to get is 0.688 moles of O2 for our species. Now, what can we do with that from here though? We were given a couple other things. We had temperature, we had volume. So let's maybe highlight those. So we had a volume, we had a temperature, then we're trying to find total pressure. So from all those pieces, it doesn't mention any change is occurring. It's just saying that there is a current system, that there isn't anything going on that's different here. So whenever that's the case, when we're looking at a current state of a gas, that's the ideal gas law. And the whole idea of Dalton's law is that all gases are very, very tiny, indistinguishable particles, meaning that they are all just little orbs wandering around in constant random motion. So if I take our moles of oxygen, our moles of nitrogen, and let's say I combine them into our container, right? So that's our sample gas. That makes up air. If I throw them both in there, can you tell the difference? Can you pick out the little nitrogens? If you look around your room right now and I start looking around, can you start picking out all the different atoms? Well, no. So what does that exactly tell us? Well, if you kind of think of that in terms of pressures, we can simply add them together to get total. But what else does that relate to? Well, that also relates to moles. Oh, that's something that's very powerful. So if that relates to moles, one thing that we can have now is a new formula where the total number of moles is equal to N1 plus N2 plus as many gases as you have. So another partial law comes into play, which is partial moles. So being that that's the case, what we can do with that, let me just add another page here, is we can use that to do more calculations. So if I take my moles, which from earlier, I can find out what my total moles in my sample are. So if we take the moles of oxygen, the moles of nitrogen, so meaning we'll take 0.688 moles and we'll add it to 0.279 moles, or not 279, 2.79 moles of nitrogen. We'll add those together. And what we're going to end up getting is the total moles of gas that's in this sample. So just indistinguishable particles that are in my sample. So why is that important? Well, we want to know what the total pressure is, which is related to the total number of moles. So now we can take all of the values that we had earlier, plug them into the ideal gas law for pressure. So let's write down our ideal gas law equation. So ideal gas law is PV is equal to nRT. We want to get pressure by itself. So we're going to divide volume out from the right-hand side, getting pressure alone. We'll have our new equation, which is pressure is equal to nRT divided by volume. And now what we can now do is plug in our values from before. We have our number of moles, which we just calculated. We have the ideal gas constant, which is something that is well known. We went over in a previous video. So for us, that value is 0.08206 liters, atmospheres, moles, Kelvin. We have our temperature, which for us is 28 degrees C. We have to convert that to Kelvin. So that would just be plus 273. So that'll come out to about 301 Kelvin. Okay. And then we'll divide that by the volume of the gas, which was 19 liters. Okay, this is a long problem, a lot of moving pieces as we're going through this. So when we solve, we'll do 3.48 times our constant times 301, solve it, then divide by 19. Now, when you do that, you're going to get a total pressure of 4.52 atmospheres of gas. So this is all the gas that's in our sample, and that is our final answer. Fantastic. That's exactly what we want. Now, what else can you do with this? Well, what if I asked you what is the partial pressure of each gas? Can we do that? Can we actually figure out the individuals, right? So being that this gas is essentially the total gas is equal to the pressure of each of the gases combined. So in this case, it's P1 plus P2, aka nitrogen and oxygen. Can we figure out the individual gases? Well, we can. So I'm going to go into a little derivation for ourselves. So another skill of how to use the combined gas law for different purposes. And what this is going to show is a new equation. So in this sample that you have of air, temperature and volume are already described, and they're not changing. They are in a constant state. But the same thing can be said with moles and with pressure as well. Well, is that entirely true? Can we define that maybe a little differently? Well, we can. One thing that we could do is use the law of use the law of the combined gas law. Meaning, if I take P1V1 and I do the expanded version, so including moles, so P1V1, N1T1, and instead of me saying P2V2, why don't we instead say, oh, well, we have the total number of pressure, the total volume, the total moles, and the total temperature. Well, the thing about this is temperature and volume are constant. So when they are constant, they end up canceling out because they are not changing. N1, if you remember from our original problem, was a really tiny value. N total was also very big, so that was changing. So what happens is these go away. And as a result, it ends up giving us a completely different and usable law in a sense. So P1 N1 is equal to P2 N2, N total, or P total N total. And what we can go around from there is we can try to rearrange this thing in a sense where we can actually find and utilize it to become not only this equation, but what it can eventually lead to is molar fractions. So what do I mean by what is a molar fraction? Well, if I rearrange this equation where I times both sides by N1, so when I do that, N1 will be on the left-hand side, and I'll get N1 over N total times total pressure. This term here, you can commonly see in textbooks as the letter chi, which represents the molar fraction. So it's how much fraction of gas is in your sample. So with that all being said, how can we figure out the partial pressures? Well, we can use our different amounts of moles from our original problem. So in the very beginning, in our first one, so if I have, let's say, the partial pressure of nitrogen, well, we know the total amount of gas was 4.52 atmospheres. And what we also know is we can see how much the moles were. So the individual moles were 2.79 moles all over 3.48 moles. So what this is the partial divided by the total times our total pressure. So this is P1, or sorry, not P1, N1 all over N total times total pressure. So what we can actually get here is that our partial pressure for nitrogen is going to be 3.62 atmospheres of N2. And we can do a very similar idea with oxygen as well. We can take our partial moles of oxygen and end up plugging that into the equation too, and do the same type of calculation. So if we take that 0.688, divide by 3.48, times it by the total pressure that is there, we can also get what the partial pressure is of oxygen gas. So this is something that is a very powerful method. It lets you do partial pressures, partial moles, everything, all in one equation. So one last one. So if I have a very common experiment, so with this one, I have magnesium metal and it reacts with hydrochloric acid. This is something that's very commonly done in most introductory chemistry labs. In fact, you most likely did an experiment like this semester. So if magnesium metal reacts with hydrochloric acid, what's going to happen is the magnesium metal that we have in here, it's going to be reacting with all that HCl. When that happens, hydrogen gas is going to be created. It's going to displace all of this water that's in the tube. So this is being collected over water at 26 degrees C. So one thing about this is at atmospheric pressure, which is at about 758 millimeters of mercury. I want you to determine the mass of H2 collected. So how can we do that? Well, here's an agenda for ourselves. We are given a lot of different pieces of information. We have the volume of hydrogen gas. We have the temperature of the water. We also have the atmospheric pressure, as well as a partial pressure. So what are we trying to do? Well, we want to determine what the mass of H2 is. So how can we do that? How can we go from all of this to everything here? Well, the goal is always the mole. So how can we try to get to moles in this case to solve for the mass of hydrogen? Well, we're given a total pressure and we're also given a partial pressure. So the first thing we're going to use is Dalton's law. So why don't we start there on our agenda? So if I have my total pressure, which in this case is atmospheres, this is going to be equal to the pressure of the H2 gas being created and the water vapor that is coming off as well. So they're both existing in the solution. So if my total pressure was 758 millimeters of mercury, we don't know the pressure of hydrogen, but we were given the pressure of water. So what we can do with that is we can rearrange this and find the pressure of hydrogen. So if we do that, we'll get pH2, which is 758 millimeters of mercury, minus 24 millimeters of mercury. So once we solve for that, essentially what we're going to be getting is that pressure. So with that being all done, we're going to get about 734 millimeters of mercury of H2. Okay, so we just did step one. Step two says, let's convert it to moles. So we were given a bunch of different values. We have a volume, which was 482 milliliters. We have a temperature, which was 26 degrees C. We don't have moles. We do have an R constant, so we can solve for the ideal gas law. So why don't we use it? So PV equals nRT is the bridge. So once we are doing that, what we need to do is rearrange it to solve for moles. And in this case, it's going to be moles of H2 in particular. So what we'll do is we'll divide both sides by RT. This will get moles by itself. So we'll have NH2 with PV divided by RT. We'll plug in our partial pressure of of mercury, so it'd be 734 millimeters of mercury. But the thing is that in the correct units? So we got to check that. R is 0.08206 liters, atmospheres, moles, Kelvin. So are all of our units correct? Well, none of them are correct. So the first thing we need to do is convert everything. So let's do the first one. So pressure. So pressure is in 734 millimeters of mercury. So how do we convert that to atmospheres? Well, 760 millimeters of mercury is 1 atmosphere. So what this will do is cancel out millimeters of mercury. And this will allow us to get atmospheres, which is 0.966 atmospheres once you divide those two numbers. Volume is going to be when you're taking the value we had earlier, which was 482 milliliters. So 482 mLs, we got to convert that to liters. So 1,000 milliliters is 1 liter. Milliliters cancels. That will give us 0.482 liters. Temperature, it was 26 degrees C. We'll add 273 to that. And that'll give us 299 Kelvin. Okay, now we can plug all these values in. So with that being said, we'll plug everything in. So we have the atmospheres, we have our volume, we have our R constant, which is 0.08206. And then we also had our temperature, 299 K. Once that is solved, this will give us our moles of nitrogen, so NH2, and what we will get is 0.01897 moles of H2. Now, are we finished? Well, our last step was to convert it to mass. How can we get to mass? Molar mass, right? We got our goal, which was the mole. Once you get there, you can convert it to anything you need. So in this case, to molar mass by using H2's molar mass. So we'll take our moles of H2, and what we're going to do is cancel out moles with the molar mass of hydrogen. So when you take 2 hydrogen atoms from your periodic table, multiply 1.008 times 2, that'll give you 2.016 grams of hydrogen. And what that's going to tell you is that in your tube from your experiment, you got 0.0383 grams of hydrogen collected. And that is an extremely tiny value that you collected. So that was a very involved problem that went from you converting, that did moles, partial pressures, that had all of it in one problem. So partial pressures are something that can be very, very applicable to many situations, and I wanted to cover all the bases. So hopefully this video will help you on future homeworks, on concepts to study for exams. So I try not to hold back on harder problems here. So I hope this helps. Let me know in the comments what you thought, and if you want anything else in the future, please hit that like and subscribe button. And thank you so much for listening and just being here to support. I'll see you all later, and have a wonderful rest of your day. Bye now.